Okay, welcome. So let's start our lecture. Everything's okay. Right. Good morning. So let's do a quick summary, quick recap from last time. All right. Last time we talked about the equilibrium, right? We introduced the mu. Mu is a chemical potential and correlate the mu and the G and some information derived from some mathematic tool, all right, like homogeneous function. And then we found that several relationship between chemical potential and the G and also U, and how we define the phase equilibrium, what's called equilibrium, all right? And then we took a step before the equilibrium, and then we can find that mass is flow from mass flowed from higher chemical potential to lower chemical potential. All right, so we're using mathematic proof to show that, and then we talk about Gibbs phase rule, and then we know that for certain constraint, you can only have certain range of the variation of your phase. For example, triple point and two-phase line and one-phase plan, for example. All right. And then we talk about mixing process for ideal gas. Mixing process for ideal gas, we have two things that we need to examine before we actually did that. For pressure, we found that the pressure for each gas composition is the molar fraction times the total pressure. Okay, so last time we obtained this, and then for the Gibbs functions, how it mixed. Actually, this is quite simple. The Gibbs function is actually the summation of Nj times Gj. Okay, and then we use a lot of existing knowledge from like review 1 or previous few pages, and then we found that each G is actually equal to RT times natural log P plus phi. The phi is bunch of constant, and the constant is combined by Cp, H naught, and temperature and S naught. All right, so all of them are all constant. So then we are ready to see the procedure along the mixing for ideal gas. All right, and then initial condition has two separated gases, and then you can see that the Gi is actually I is initial. G is actually summing up the both condition together, N1 G1 I, N2 G2 I, and then also we use the equation obtained in the previous page, so we can write it down like this. For the final state, we also can write it down like this, and then the thing is different because now your G1 can be written by this, G2 can be written by that, but the P1 and P2 can be rewritten as the molar fraction for each gas composition to the times the total pressure, and the same as the second term. All right, and then so we can find that GF is blah 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 blah, and then we compare the information we obtained before, and then we found that okay, mu is a chemical potential is actually G plus RT natural log X. So in the mixing process for ideal gas, the chemical potential for each gas composition is g times RT natural log x. The x, of course, is its molar fraction. All right. So now we are ready for that. So now we written down GI and GF in the previous page. Okay. So we kind of combine the GI and GF into the same equation. So GF minus GI is of course delta G. So the delta G written down here and GI written down here, minus together. Okay. And then we notice that we know mu1 and mu2 is actually mu1 equal to G1I plus RT natural log XI, right? This is obtained from the previous page, right? So we know that. Mu2, we also know that, right? And then we compare a little bit, yeah. N1 G1I, N1 G1I. Oh, so you can cancel that. And N2, cancel. Okay, so you find that the only thing left, well, it should be 1, sorry. It should be 1. X1, not I, X1. Well, because X won't change, right? X1 has no X1I or X1F because X doesn't change. The molar fraction won't change, sorry. So it should be 1. All right. So we substitute to mu1, and then we notice that, okay, the thing left is RT N1 natural log X1, N2 natural log X2. All right. Then we can write it down further. MRT X1, X1 natural log X1 plus X2 natural log X2. Okay, by using M times M1 equal to, well, M times X1 equal to M1. All right. M times X2 equal to M2, because this is a molar fraction, right? So you see that, and you find that X1 and X2 are all positive because they are fraction. Fraction must be 50%, 90%, never be negative percent, right? So X1, X2 are positive number and less than 1, between 0 to 1, right? So it means that delta G must be less than 0 because you see this one and that one always negative because it always between 0 to 1. So the natural log to 0 point something, it always become negative. Negative. So delta G must be negative. All right, so it's kind of, makes sense. Going to the equilibrium state to minimize the delta G. 好，我们讲混合嘛，上一次我们讲到要在混合之前，我们要先算一下，它的 pressure 是怎么样变化的，怎么样表示的，然后 G 是怎么样表示的。那我们上次就讲到说，初始化的 G 长这样，结束的 G 长这样子。那它们两个相减以后呢，就会发现，就写出来了哈。然后 mu1 又等于这个比较难的式子，就会发现它们前面两个会消掉，消掉完以后，剩下 delta G 就只剩下这一个项 RT N1 natural log X1 跟 N2 natural log X2。OK， 所以我们就把这个 N1 把它写成 N 乘上 X1， 因为 X1 就是摩尔分率嘛所以说 N 乘上 X1 不就等于它的 N1 的值吗 ？N1 的摩尔数，对不对K 摩尔。好，那接下来算到后来 delta G 会等于长这样子。那这就发现 natural log x1 跟 natural log x2 都会是负的，为什么？因为 x1 都是0到1之间的数字，因为它是50% 嘛，60%、90%，不可能会有负的，所以说它一定都是0到1之间的数。那这样在 natural log 里面来说，它就是负的啊，它是负的，它是负的，所以 delta G 永远都会是负的。OK， 那它就表示说我们 delta G 只要会往下降，表示它要去 reach， 它要去到一个平衡状态。All right, next one, entropy change in mixing process. So what kind of entropy change in ideal gas mixing? So the S equal to something like this. Although it looks like not that familiar, but actually we mentioned that before in page 8. This is one of the reciprocity relation. Okay, this is one of the reciprocity relation. So you can obtain that in page 8. S equal to partial G over partial T as constant P and with the minus sign. All right, so delta G is actually the change of the G, no problem. Okay, and then you find that the delta G is also equal to what you learned in the previous page. But now you need to do the temperature differentiation. So, nothing T here. So it becomes delta S equal to blah, 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 blah. Again, you see that X1, well, X1, sorry. Hey, X1, X1 and X2 always in between 0 and 1. So it also makes delta G greater than 0. Oh, by the way, this is minus minus. So you got more minus for the delta S. Okay? Here, no, is a positive. Right? So minus. Okay, so it makes delta S always greater than 0. So the mixing process will make the entropy go up. Very makes sense, right? Very good. And then one exception we can mention here is that how about two gases with equal volume are the same, which means that gas 1 and gas 2 are all the same. And then they also has equal volume. So which means that actually, if you take out of the wall between them, actually they are all themselves, right? So they doesn't change anything. Okay, so in that case, actually, delta S should be 0 because they are the same, all the same. So delta S should be 0. But in this equation, we didn't consider if the X1 and X2, I mean, the gas 1 and gas 2 are the same. Okay, so even when we do this, we find that delta S, yeah, greater than 0. But if they are the same gases, the entropy change or Gibbs function change should be not 0. If they are if they are the same, Gibbs function and delta S change should be 0 because they has exactly the same equilibrium state, and when we take out the wall, they are still exactly the same for the equilibrium. So it is a paradox. It's actually not make sense if we apply this equation. All right. So this is kind of disadvantage of the classical thermodynamics because it doesn't take into account the possible states. It will be resolved in a new version of the thermodynamics, statistical thermodynamics. All right, in the next few pages. Next few chapters. All right. 好，那接下来我们刚刚讲到了Gibbs function 的改变，在混合的话，那如果是 entropy 呢，会有怎么样的现象呢？我们把 S 写出来 ，S 跟 G 的关系找到，怎么找呢？找 第八页的互补的关系，然后我们就会发现我们的 S 会写成这样，那这 delta S 那当然就是 delta G 咯。写完以后呢，我们把 delta G 的公式带进去，上一页哈带进去，结果就发现它必须要做一个微分 T， 微分 T 就不见了，所以这个式子跟前面那个式子就是差一个负号加微分T 被微分掉了。那之后我们再看 x1、x2 还是一样是0到1之间，所以它这边是负的，但是中间外面多了一个负号，所以负得正，所以 delta S 大于0，永远大于0，表示说你只要混合的状态下，混合 ideal gas 状态下，绝对都会是大于0的状态。好，那这时候有一个小问题，就是说，如果今天有2个相等体积，然后的气体是同样的气体，那都是在相同的平衡状态下，你把中间的板子、中间的墙拿掉，它的混合其实跟没有混合是一样的道理啊。所以两边都是一样的气体，两边都一样大，两边都等效，那就是平衡。一拿掉，哎，完全跟之前一模一样。所以说理论上来讲，这样子的 delta S 跟 delta G 都会等于0哦，因为它没有变化，没有任何的变化。可是如果今天带刚刚这几个公式来看，它终究还是会大于0，那表示说这个传统热力学的这个式子并没有考虑到2个气体到底是不是一样的这件事情。OK， 所以它不管怎么样，它都会给你2分，就是让 delta S 大于0。那这就是一个比较矛盾的现象啊。那这个东西在传统热力学是不对的，是矛盾的，但是在统计热力学里面，我们就会解释到为什么它们2个加在一起，同样的东西加在一起它不会让 delta S 跟 delta G 就是改变。那原因是因为他们其实2个人的可能的状态都是一样，那所以它看不出来到底有什么变化，那自然就可以解释这个问题。所以表示说，传统热力学终究还是有一点点没有考虑到的地方。OK，next. Finally, the final stuff, final section for the PDF 3 is the third law. The third law, there is a lower limit to the temperature that can be attained by matter called absolute zero of temperature. Okay, 绝对零度. And the entropy of all the substance is the same at the temperature. Okay? Well, the definition for the entropy is actually the absolute value of the entropy is actually 0 to T d bar QR divided by T. Previously, we only add this, right? But actually, we always kind of neglecting the integrating factor term called not integrating factor, integrating constant, sorry, S naught. S naught is actually the additive constant at 0K. Okay, this is additive constant. You can also in the mathematics you can also see that integrating constant. Okay, integrating constant. So S naught, what is S naught? Actually, the S naught is the entropy at 0K. Okay, and actually this is the limit, right? Actually you in the human being, you can set everything as 0. So we also can say, okay, the S going to 0. Planck's statement. Okay, Planck's statement called limitation to temperature to 0. The entropy should be 0 as well. Okay, and the proof is in page 172 in the text book. All right, in the textbook. So you can go to see that the limitation, the temperature to 0, the S equal to 0. Okay, and what we are going to talk about here is actually the thing called Nernst theorem. Limitation to T to 0, S1 minus S2 need to be 0. So you have two things. For example, two ideal gas. All right. One, gas 1, it has S1. Gas 2, it has S2. When it go to 0, their difference should be 0. The entropy of these two gases should be 0. So we it called Nernst theorem, and we want to prove that here. Okay, because this is a kind of difficult to understand. So I just pick it up and then explain to you in the course. And to prove this, we need to based on a postulate, an assumption that the absolute 0 of temperature cannot be achieved by human being. Okay, so Nernst postulate, Nernst postulate is Nernst assumption. Assume that 0 absolute temperature cannot be attained, cannot be reached by human being. Well, it's kind of understandable. Our human being, people, cannot reach the limit. Always, you know the calculus, right? You always cannot, you cannot get the 100% limitation. You will never do that, but you can get close to it, right? So you never going to achieve the limitation, but also means that you don't have limitation. Wow, that's really philosophy. All right, anyway, I'm just saying that people has our own limitation that we cannot reach the limitation. All right. So then we are going to use this postulate to prove this. OK， 好，我们就讲第三 law。第三 law 就是有一个绝对零度对于我们这所有的材料，那大家到了那边以后，它的 entropy 都会是一样的值，这是它的 third law。那至于这个一样的值是什么值呢？ Well， 没差，反正数字是人定的嘛，所以你只要定义成0都可以都可以哈，反正 Planck statement 就是 Planck 就说它是0，好，那我们就定义它为0不管它。那更多的解释在第172页，在书上，所以你可以回去看。总之，这个0值是我们自己人类给予的总之它就是一个最低的值，它就是一个最低的极限。好，那我们更有兴趣的反而是说就是这个 S 它其实写成这样嘛它这个 S0 它就是我们的积分常数，这个积分常数就是 0K 嘛是 0K。应该说这一句话就是这是 third law 把它写成数学式子而已啦那至于我们要怎么样把 S0 证明说它是为0，那就是172页的事情。但我们想要证明的就是说，任何的东西跑到任何两个气体或东西材料到达0点的时候，绝对0点的时候，它们之间的 entropy 会是相差等于0。OK， 那我们要去证明这件事情，课本上有写，只是学长姐觉得说看不懂他在写什么。好，那我们就拿出来讲。那要证明这个 Nernst 的理论呢，要借助 Nernst 的假说。这个假说就是对于人类来说，绝对零度是永远达不到的。好，达不到的。我们用不管怎么做，怎么用，不管怎么去怎么讲，不管用什么样的流程都是达不到的。好，那这其实也蛮正常的，因为就像微积分一样，你的极限你只能越来越靠近它，但是你是永远无法达到这个极限的。那换句话说，我们也是没有极限。 好，蛮有趣的一件事情，这是我最近才想，就是今天早上在准备这堂课的时候才发现，人类是无法到达极限。那换句话说就是没有极限。哎呦，还蛮好玩的，就是你永远都可以变得更好，但是你不可能最好。哎，就这样，还蛮酷的。好，so next week, next page, we want to prove that delta S naught equal to S naught 2 minus S naught 1 equal to 0, which means that this entropy, gas 1, gas 2, the differences between them should be 0 at 0K. Okay, so we want to prove that. And we also need to know what we know. Absolute zero temperature is unattainable. Okay, human being cannot do that. The definition of S equal to S naught, yeah, this is the third law, right? We wrote to that. And then, because we are going to decipher the Q here is actually related to CP or CT, right? But here we don't say, sorry, CP or CV, okay? But here we didn't say anything, CP or CV. We didn't take anything symbol here because this figure won't change if you writing down CP or CV. They all looks like this, so it doesn't matter. Okay, so you can write CV or CP, both are okay. So I just take out the subscript. All right, so here can be transformed S equal to S naught 0T integration C divided by T and do the integration for dt. So now we want to do we want to prove this one is well, SO2 need to be equal to SO1. We want to prove that, right? But it's really difficult to prove that. So we want to do the logically inverse way. We want to prove that S1 and S2 not to equal to each other are impossible. Okay? Well, it's impossible. So we want to prove impossible. We want to prove SO1 and SO2 are not equal. It's impossible. So which means that SO1 and SO2 need to be equal. Okay, so this is a strategy that we're going to do. Okay, so now we assume that S1 and S2 is greater than S1. We assume that and then prove that it is impossible. Okay, so this is the strategy. So S2 greater than S1 always. Okay, so you can see SO2, SO1 greater than SO2 greater than SO1, even at temperature equal to 0. Okay, absolute 0 value. So it must be looked like this, as entropy and temperature, and it's going this way and that way. All right. So if we write down this value, this curve, S2, S1, it will come up this line. OK， 好，我们要讲的是，我们先要证明啊，SO1 跟 SO2 相减以后等于0。O 的意思就是说在0K 的时候 ，OK， 好，那我们必须要先知道一些状态，就是说绝对零度是达不到的。再来就是 S 的定义就是 S0是积分常数嘛，好，然后后面是这个的定义。那这个定义呢，这个 Q 我们要去使用它的时候，我们通常都是用 CV 或 CP 来做积分嘛，对不对？好，所以我们把它改成这样子的写法。但这边可能没看到 P 或 V， 为什么？没关系，原因是因为你这边写 C 写 V， 它的图都长这个样子，都长这个样子，那只是值会差一点而已。所以我们这边不写 P 或 V 反正它就是会长这个样子。OK， 好，然后接下来呢，我们要证明一件事情，就是说，我们原本想要证明就是 SO1 等于 SO2， 对不对？它们相减等于0嘛，但是这很难证。所以科学家就想到一个反证法，就说我们先证明他说 SO2 跟 SO1 不等于，然后再证明这个不等于不可能，那就一定等于这样的意思。好，所以我们现在来开始证明，就是说我们现在这一步要证明 S2 大于 SO2 大于 SO1 的状况是不可能的。然后接下来我们再去证明 SO1 大于 SO2 也是不可能的，这样子 ，OK， 这样它就一定相等。好，这就是我们的策略。Alright, so firstly we want to prove that SO2 greater than SO1 is not possible. Okay, so figure looks like this. So let's take a look. Cooling from temperature T1 to T2 by an isentropic reversal process. Okay, so you see this is two lines. If you start from S1, I want to make the S1 has the same entropy value. I can do an isentropic reversible process to make the S1 go to S2, get the same value. Okay, so you see, if the SO1, SO2, I want to make it equal. I want to make the S1 has the same value of S2. Actually, we just need to do the SO1 plus 0 to T1. And you can see that we're just changing the entropy, we can achieve that. And if you can agree with that, the entropy can change until the gas 1 equal to S2. Okay, so this is possible. If this is possible, why not? We can move around this process up or down. If we can do that, why not we just reach to the point that after the isentropic process, you can reach SO2. Okay, so which means that actually this equation is possible. Is possible. Okay, so if you choose this process, then you reach SO1 and make it is O2 and O1 are the same. Okay, so which means that this violates your assumption before. 好，我们现在要讲的就是我们看这两条线，这两条线你会发现绿色这个点是 S1 的 entropy， 蓝色这点是S2 的 entropy。可是我们想要让它，就是你看哦，这两点它们是同样的高度哦，它们是同样的高度。那这时候你可以看到，就是说这两个是同样的高度，所以它的 S 会相等嘛，对不对哈？所以你看到蓝色的点叫做 S02到就是加这个积分式，然后 S01加 T1 这个积分式在右边，它们是相等的 entropy， 所以它们会相等，对不对哈？好，那这时候呢，我们把它稍微移动来移动去，把这个东西移过来，然后我们就会发现它写成这样子。好，没什么不行吧，对不对哈？这个式子是应该是可行的，对不对哈？好，那这个 process 既然这边可以，那为什么不选上面一点，或是选下面一点呢？可以吧哈？上面或下面都可以，对不对？所以说，如果今天我选到了这一个点，刚好会到让这个 SO2 到达 T 等于0了，正好把它就是到这一点，那不是表示说，你是可以跑到 SO2， 可以跑到那一点嘛？就是你可以达到0的那个点，那不就跟你之前的状态有关，就是你假设是不一样的吗？好，你可以看到，这边我这边写一下哈，等我一下 ，SO2 加这边0到 T2 快，可是如果你选到了一个最后这个动态的话 ，T2 快就会等于0了，所以这边就会变成0。OK， 那这时候你就会发现哦，SO2 等于 SO1 加 这个东西。OK， 那这不就代表说你已经可以用这样子的 process 达到 zero and 就是什么零的绝对零度 ，OK？ 那这样子不就违反了你的那叫什么 unattainable 的 principle 吗 ？OK？ So you can see that if you choose this, you find that if you find this one go to here, it makes 0 to equal to this one plus this. So which means that it is 0 is attainable. Okay? And this, you can see this one is actually SO2 minus XO1 equal to this, which means that SO2 minus SO1 greater than 0. Okay? So this is possible. This is possible. And also means that absolute zero can be reached by this process. But it's not attainable. So, which means that you cannot do that. You cannot do that. So it must be SO2 minus SO1 less or equal to 0. So you need to transfer to make it prove another step S1 greater than S2. And you do exactly the same. You find that nothing can make it possible. OK， 好，我们讲这边有点开始有点绕口，我知道英文这样听起来一定听不懂。好，没关系，我们来看看哈，就是说啊，哈，我们前页不是说我们如果选到这个状态，它可以到有相同的 entropy 的话，这两个有相同 entropy 的话，那我们就可以把这式子写出来。我们把这写出来以后呢，你看左边的跟右边的相等嘛，对不对哈？然后我们就把这个 SO2、SO1 拿到右边去，我们就会发现它写成这样子。那可是这边这个在到达 T2 的时候 ，T2 等于 T2 换等于0的时候，它这边会等于0哎，好，这边会等于0，这边会等于0的时候，我们就会发现 SO1 减 SO2 加上这个东西会等于0哦。好，这会等于0。好，也就是说，也就是这个式子。那这个式子，我再把这个东西移到左边去，我们就会发现 SO2 减 SO1 会等于这个东西，就表示说它大于0哦。那这跟你的假设是一样，那表示说，哎，你真的可以用这样子的 process 到达0度哦，因为你都很符合你现在所有的假设的条件，那可以到达0度，那不就代表就突破人类的极限吗？所以它是不行的。不行的状况下就是说，哎，表示说你现在这件事情是不被允许的。那不被允许的话，我们要达成一样的状态，就只有就是要换另外一条路走。好，那我们假设 S1 大于 S2 好，那重来做一遍，你就会发现，哎，还是一样 ，SO2 还是可以到 S1、S2 还是可以做一模一样的事情。那这也是就是 attainable 啊，表示说它还是可以到达最底部。好，那这时候表示说这两个都不行。好，你不能 S1 也不能大于 S2 也不能大于 S1 啊，大概是这样。那 OK， so what I'm talking about is that firstly you assume that S2 greater than S1 and the process can be done because all the equations are all reasonable. So human just follow this equation and then we can achieve temperature 0K. But no, we cannot do that because 0K is not achievable by the assumption, okay, by the human being assumption, calculus. So which means that S2 cannot greater than S1. So now let's go to the second step. We assume S1 greater than S2. But we know that we will have exactly the same conclusion. We can have the same conclusion that we cannot do that because which means that we can achieve 0K. So combine both condition. SO2 need to be equal to SO1. All right. And then we notice that SO2 need to be SO1, need to be looks like two curve and meet at one point. Okay, and then you can see you can see that yes, S1 and S2 need to be like shrink to 1 point, but the value can be any, right? So if we combine with the blank statement, and it will shrink to 0. Okay, I mean human can set every value, so you can see that if we follow this equation process, yes, we can do that. We still can do that. We can still do that. We can still do that. We can still do this, but we found that every step we need to go like this and that and this and that and this and that, which means that we will never reach the final point. Okay, each step of getting smaller and smaller. All right, so that's how we cannot attain the zero K. 好，那接下来就讲就是刚刚讲到，我们假设 S2 大于 S1，然后发现，哎，那这样就可以到达0K 啊，这样不行，那我们赶快反过来 ，S1 大于 S2，哎，那这样还是得到一样的结果，还是可以到达0K，那就发现一定要 S1 等于 S2 在0K 的时候，一定要这样子，一定要把它到最后就是聚集在一起，这样它才可能没办法到达。那你会发现，真的，你看只要。它的确是可以从 S1 S2 有相同的那个 process， 但是它每一次都必须要，它如果要往下走，它一定要往下降，再往左边走，再往下降，再往左边走，就变成一个 step。你的 process 必须要一直往这样子走，那它就会永远达不到了哈。那就跟我们的假说是一样的道理。Okay, so this is the final page of PDF 3. And we finish all the range in midterm 1. Okay. The midterm 1 should be 29th of October. All right. So be prepared. But because we don't have much time, so I need to proceed to chapter PDF 4 and 5 or 6. All right. So each midterm is containing 3 PDF, 1, 2, 3, and 4, 5, 6. And 7, 8, 9. All right, so something like that. Now we finished the review 3, and let's continue to kinetic. It's not review, it's a new chapter. Let's go into statistical thermodynamics now. Okay, so kinetics. Kinetics means, well, kinetics is not statistical thermodynamics. It's actually a kind of entrance level. You need to learn kinetic first, and then you can understand more about statistic thermodynamics later. All right. So kinetic theory. Kinetic theory is about motion. Okay, about motion. This is about motion. Well, you see, classical mechanics has statics, dynamics, and the dynamics is really can be connected. I mean, or has two subgroup, kinetics and kinematics. Oh, what does that mean? They are all dynamics in Chinese translation. All right, but this is a little bit different. I understand this when I was studying in UK, the UK, England. Okay, and my supervisor told me kinematics is actually not related to motion. It related to position, positive position. So you see, kinematic describe the motion of points, bodies, and without consider the cause of motion. All right, what does that mean? Which means that you only consider, for example, you can see this truck with the machine robotic arm, right? The robotic arm has the degree of freedom, how it rotates, how the length of it. So you can calculate the motion of this point, maybe point A, where can the A goes? Okay, so the limitation of the angle and length for each joint will limit the position, the motion of this point A. So this is called kinematics. Okay, so we're not talking about this. We talk about kinetic with the velocity, with the direction. Okay, but kinematic does not. All right， 好，我现在讲一下 kinetic 就是动力学，但是实际上有另外一个东西 kinematics， 中文翻译好像也是动力学。我在大学在念力学的时候，我发现我把这两个搞混了。我到了英国念书的时候才发现，哦，原来他们不一样。我老师教我说 kinematic， 你可以看到这个 Wikipedia 写的哈，动力学其实有分两部分，一个是 kinetic 跟 kinematics。kinetic 就是等一下要学的，跟速度有关，跟力量有关 ，OK， 跟方向有关。但 kinematic 不太一样 ，kinematic 是说这个东西它的位置在哪里，然后它受到什么样的限制，什么样的条件限制，例如说它的角度可以转多大，像我的手我不能把它转到后面去吧，对不对哈？因为我的关节有自己的限制。kinematic 就是在讲说这个东西，这个系统它可以到达的状态是它能动的状态的范围在哪里，但是它不会去管说它怎么到达那里，所以有一点点像是 classical thermodynamics 的感觉，但 kinetic 不一样 ，kinetic 就是它会告诉你说它是有受到什么样的力，然后它有什么样的速度，然后到达那里所以这两个有点差别。那当然 kinematic 相对来说应该是会比较简单比较简单，因为它就是在讨论一个东西的一个系统的极限在哪里，它的范围在哪里。Okay, so kinetics is what we are going to learn. So in order to solve the limitation of classical thermodynamics, we consider structure of matter. Okay, remember we talked about classical thermodynamics. We say that we know it will happen, but we don't know the cost. We don't know how long will it take, right? But kinetic theory can tell you one step by step. Okay, we want to firstly consider every system has small particles, small particles, small atoms. So statistical thermodynamics is best to treat the quantum mechanic point of view. Okay, so we firstly treat kinetics, learn kinetic theory, and then we consider quantum mechanics later. So now kinetic theories concern the motion of molecules, motion of atoms, okay? And then we will know what happened. And also we're considering the probability, okay, or chance, okay? 好 ，kinetic 就是动力学，我们基本上就是要进入统计力学的第一关它还不是统计力学我们考虑它分子的动态。好，那我们今天就不是这一节课上到这里。I will see you after 20 minutes, and I will continue our lecture. Thank you.
真的影响你什么事情？就是你会懂出去。完成的事。
All right, let's continue our lecture. Right, so before we entering the statistical thermodynamics, we need to learn about the knowledge about knowledge about kinetics. All right, but before we learn about kinetics, we need to have some assumption. Otherwise, it's too difficult to calculate by hand. All right, so you can see that all this knowledge is from kind of ancient, like 19th centuries, something like that. So we don't have they didn't have computer at that time, so they need to calculate by hand. So because they are dealing with a really big number of molecules, so they need to have some assumption to simplify the calculation. All right, so that's how we trying to do here. So firstly, the fundamental assumption is that one, well, I don't know why it becomes so big, but I hope you can accept this. One, a macroscopic volume contains a large number. Okay, large, so many, large number of molecules. Okay, so why they give this assumption? Because it knows that they know that the N here is 1 kilomole, right? So the Na becomes 6.02 times 10 to 26, 6, not 23, 26, all right? Because it is kmole. And we know that typically our experiment is done at temperature 273 K or well 0.15 K, and the pressure is 1 atm. All right, and also means 101.3 K ha. Okay, so if you have this, you can easily calculate the V here, which is 0.314 times 273 at 1.013 times 10 to 5 equal to 22.4 M3. So now this is a really a kind of important value that STP value for volume. What is STP? Standard temperature and pressure. This is temperature, standard temperature, standard pressure. You got value, volume as 22.4 M3. All right. So in this volume, you have such many molecules. So approximately, you have 3 times 10 to 25 molecules per meter square, meter cube. This is really, really big, right? Really, really big, 10 to 25. Big number. Yeah, so large number of molecular assumption is very makes sense. All right. The second assumption is that the separation of molecules is large compared with molecular dimension, which means that they separate very far away. Okay, far away. So what can we validate this assumption? So at STP, which is 22.4 meter cube, divide by 6.02 times 10 to 26 equal to 30 times 10 to, well, minus 27 meter cube. And if you want to see, so which means that this is kind of average volume occupied by one moleculus. Okay, occupied by one moleculus, the average volume. So if we treat that as a cubic, so we take its cubic root. So you can say the distance between the molecular averagely is cubic root become 10 to 3 times 10 to minus 9. Okay, minus 9 m. And the distance, diameter of a molecular gas, typical diameter of the molecular gas is kind of divided by 10. So it's 10 times of the diameter. So you can imagine that this gas has about such big, and then the distance should be 10 times of this. All right, so it's kind of far away from each other. It's kind of large, 10 times of its. So like our distance, like 10 diameter of ourselves. All right, so quite far away from it. So get for gas, okay, but for liquid or solid, molecular has nearest neighbor at a distance or slightly greater than d. Well, this, so you can see that this is a gas, and this is, if we are talking about liquid or solid, your assumptions too cannot be validated. Yeah, because you can see the solid like crystal, their structure looks like this, right? So their atoms, their molecular size is very similar to their distance. So solid and liquid cannot make this assumption. Right, so here in the gas, because they are so far away from each other, so their interaction can be neglected. But for liquid or solid, the internal forces need to be considered. All right, 好，我们要讲的是在学动力学之前，气体动力学之前， 我们必须要先有一些假设，因为古早人是没有电脑的，他必须要用手算，所以他用手算必须要做一些简化，也就是一些假设才可以算得下去，手才算得出来啊。所以你就会发现，第一个假设就是它容器里面有非常多的分子，这来看看是不是合理啊？哈，这个假设是不是合理？我们看到1K 沫里面有这么多10^26次方。那在标准的气压跟温度下呢，也就是273跟1 atm 里面，我们看到它的 volume 其实是22.4啊，这个数值蛮重要的哈，22.4的立方公尺，这数值蛮重要的啊，请自己算一算，然后背起来啊，或者是都看你怎么得到这个数字。然后我们就会发现呢，哈，这样子这个大小里面，每平方公尺里面有3×10^25次方科瓦，超多哦，所以这个还蛮合理的。接下来我们再来看，去计算每一颗平均占据的体积是多少？是30×10^-27次方立方公尺。那这时候我们那是立方，那是一个正方形的体积嘛，哈，我们想要看它的一个边长，就也不是除以，就是开立方根，就得到3×10^-9次方公尺。这个大小通常就跟你的原子的直径大概是10倍左右，的确它是离10倍的远，所以蛮远的哦，蛮远的，所以我们就可以假设它没有任何的交互作用。那如果今天是液体或气体的话，它们的晶格有一定的结构，它们的结构邻居很近，大部分都会是大概就跟它们的距离大概就跟它们的直径是差不多的哦，所以说它们很近，它们之间的交互作用就必须要考虑。所以 liquid 跟 solid 固体跟流体是比较难的科学，所以在近代才比较可以算得出来，以前的话是算不出来的。Okay, continue. The third assumption. No forces exist in between molecular. Yes, because they are far away from each other, except those associated with collisions. They will bump to each other. Okay, they will bump to each other. But they have further assumption. No duration time because they assume that the traveling is so fast. So fast. Okay, very fast. No duration time. We only talk about the average distance between the collision is mean free path. Because the time is so small, the duration time between each collision is so small. So we don't take the time as our measurement for the collision, bumping. We only consider the average distance that not in the bumping. Okay, so it's called mean free path. All right, the fourth one, the collision are elastic. Okay, momentum and the mechanical energy are conserved, so no energy loss. We assume that this is perfect bumping, perfect collisions. So energy is conserved, perfect bumping, perfect collisions. And also the fifth one is the molecular are uniform. The distributed. What does that mean? Within container, which means that their spreading are equally chanced. Okay, no preference for corner. No. Every point has equal possibility to appear at that point. All right. The directions of the velocity of the molecule are also uniformly distributed. Okay, the direction of their traveling will always uniformly distributed, which means that 360 degree, all the degree direction has the same chance. All right， 好，我们要讲，就是说他们还有3、4、5、6个假设。3是什么呢？就是说他们之间是因为太远了嘛，哈，所以他们不会有任何的交互作用，除非他们撞在一起，蹦蹦蹦撞在一起，因为他们飞来飞去嘛，他们一定会碰到彼此。但是因为他们飞的速度太快了，所以我们就不假设他们中间有飞行的时间，这有点吊诡，因为它实在太快了，去考虑它是没有意义的。反而是我们用另外一个方式去考虑它们之间的撞的频率或者是几率。我们考虑的是 mean free path， 也就是说，在撞跟撞之间，它平均跑了多远。当然，越远表示它越难撞在一起。我们不考虑时间，因为时间不管怎么样都太短。好，所以这边是蛮有趣的一个状态的一个算法。接下来是第4个假设是，他们撞到是完美的交换能量，他们动量跟能量都不会改变，就是他的能量就会撞给别人，别人也会撞给他啊，所以他们的能量都不会改变。好，没有 energy loss， 没有能量的损耗，当然是完美的。然后第5个就是它在一个容器里面，这个系统里面，它每一个点它会出现 atom 的几率都是一样的，它不会有任何的偏心在，例如说在角落会比较多哦，不会，它们都是完美的几率分布，都完全一样。还有 direction 方向，360度0到360度的方向都会是 uniformly distributed， 也就是说它们都一样的几率。请注意这边没有写说它们的速度是 uniformly distributed 的哦，它们的速度是随着叫什么 normal distribution 正常的分布，不是 uniformly distributed， 这是要小心。这边是分布。本体的分布跟方向的分布，他说 direction of velocity， 它不是说 velocity 哦，那这边要记住 ，notice that here direction of a velocity are uniformly distributed. You see direction of velocity. We didn't say velocity is uniformly distributed. Velocity is actually obey normal distribution. So velocity is not uniformly distributed, but direction is. Okay, so you need to be really careful. Next one. When we are talking about the internal forces between atoms, nowadays we're using molecular dynamics. This is advanced simulation mathematics, simulation tool. Okay, this is not related to statistical thermodynamics or kinetic of gas. No. Okay, so this is kind of supplementary material. All right, supplementary material is kind of supporting information. All right, it's not in textbook. All right, here it's not in textbook. All right, we call Lennard-Jones potential. Well, typically 2 atoms has 2 contributions for the internal force. The first one is electrostatic repulsion. The other is van der Waals attraction. So you can see the green one is attraction. The potential, if you draw the potential value as y-axis, x is r, the separations direction, separation distance between 2 atoms. Negative means attraction. Blue is what? It is repulsion. So you can imagine that if we sum them up together, the potential will looks like the red curves. And you can see that here is the most stable direction, most stable distance between 2 atoms. Okay, more stable. And also you can see that this is actually the kinetic energy that it can has, because the potential energy here, if you pull it up, which means that it has the value of the kinetic energy to fly away. All right, but of course, electrostatic repulsion and van der Waals attraction summing up together looks like this red curves, but it actually, in the real form, it should be very ugly. V are equal to blah, 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 blah. A really, really ugly mathematical formulation. But Lennard-Jones, they are really smart. They use really simple mathematical form to fit this curve. You only use two parameters that can simulate this. Okay, so you only need to specify the distance and the delta E, and that's it. Okay, so Lennard-Jones potential is kind of fundamental, basic molecular dynamic simulation knowledge. Okay, functions.好，我要讲这个是补充教材。我们刚刚不是说 kinetic 动力学都是古早在做的吗？那时候都不考虑分子间、原子间之间的交互作用力。如果考虑下去的话，根本手算不出来。但是现代我们有电脑了，我们就可以使用分子动力学去算出来。那这个东西，这都是我们的补充资料，不会考，只是我想要跟大家介绍现在都怎么做这件事情的，也就是我跟罗老师在做的事情。好，那这个叫做分子动力学，其实两个原子之间最简单的交互作用力，其实可以分成两种，一种叫做凡德瓦力跟吸力跟静电排斥力。如果把这两个画在一个势能的图上的话，我们就会发现蓝色跟绿色加总起来，其实是会有产生出一条这样子的线的。那这样子的线以后呢，你会发现，它会有一个最低的能量最低点啊，也就是说这两个原子是最适合这样子排列在，就是的距离是最稳定的。那也就告诉我们说，这个最低点的这个能量势能，如果我今天把它拿走，比方说它可以跑多快，它的 K， 它的叫什么动能是可以有多少？好，不管怎么样，总之这条线理论上来讲，用这两个式子来写，会写得非常非常丑。真正的解析的式子会非常非常可怕，非常非常丑，写很长，漏等一段。但是 Lennard-Jones， 我忘记这是两个人还是一个人了，不管了，反正就是这样的科学家很聪明，他使用一个非常简单的式子，就大略的可以去表示这样子的一个现象的一个势能的函数，也就是62。这什么叫62？就是这边这个数字。还有一个非常非常简单的式子，就可以大略的表示出这个。那既然你可以用大略的表示出来的话，我们就可以把这个式子输到电脑里面去，然后去计算每一个分子之间的最适当的位置，它会怎么跑。好，那这个式子 Lennard-Jones potential 这个式子，只要决定两个就好了，两个参数就好，一个是这个的参数，一个是 delta E 的参数。只要写出这个参数，去改那个参数，你就可以就可以大略的算出这两个原子之间什么地方才会是最准、最平衡的状态。那如果它不平衡的话，该怎么跑，都可以用分子动力学来写出来。Okay, so I just talked about the MD molecular dynamics. One of the greatest useful application for that is nanoparticle drug delivery. For example, if you have the atoms with the PEG, okay, PEG means that the polymer that can make to protect the particles. Why we protect particle? Maybe the particle is a medicine, it's a drug, right? The drug, if you want to make it work in our human body, sometimes you need to make it small, but you know, van der Waals, right? For the same particle, they will accumulate together. They will accumulate together. So it become not a nanoparticle, it become microparticle. Not good for the human being, for the treatment. So we need to put the polymer around it, okay, to prevent them accumulate too much. So which means that we need to consider the internal energy between internal force between atoms. So yeah, that's one of the most useful application for MD。好，这边要讲就是刚刚讲到分子动力学有一个最大的好处的最大好的应用就在于，就例如说你可以模拟分子之间的行为，例如说纳米的材料，纳米的药，这个药呢，它如果在身体里面放在里面，通常如果你没有做任何的保护的话，它就会聚集在一起，变得超大一颗的，因为反德瓦力它就会超大一颗聚在一起。那如果今天我们在外面放一堆 polymer 的话，就可以保护它不要过分的聚集，这样而且这些 polymer 也可以被改成可以对磁场有感觉的，所以你可以做标靶的治疗。OK， 那这就是一些药物释放的分子模拟。那等一下就可以给你看到一些例子。So this is just one really simple toy model for molecular dynamics. So the first one is without polymer, it will accumulate together. But with the polymer, it will separate it like a controllable size. Okay. So for example, this is the particle that without polymer, so it will accumulate for big microparticles, right? And you can see that we can simulate all the direction, all the motion of the particle by using MD simulation. Sorry, but this one has the polymer around it with the blue particle, right? So you can see that after the blue particle try to prevent them over accumulated, you will see that it become proper size, not combined too much. Okay, that's it. So just a small toy model, try to give you some idea. 好，我们可以看到刚刚的分子动力学模拟是简单的啦，玩具而已啦，那就是说你可以看到这边是没有 polymer 的，然后就会完全聚在一起。但如果有蓝色的 particle 的话，它就会聚集成可以控制的大小。当然，我们可以改变它的 polymer 的长度或者是密度，你就可以精准的控制 nanoparticle 叫什么奈米颗粒的大小。All right, so let's go. It was the previous 2 pages were the supplementary material supporting information not included in the kinetic theory. All right, it's just extension. Let you know not new, but more advanced tools that we are using right now. Now, the randomness of the motion. Go back to the kinetic theory. All right, randomness of the motion. Randomness motion, we talk about the velocity. Okay, the velocity. We want to determine what is the mean speed of the particle in the container, or mean square speed, or root mean square, or nth moment of distribution. We will use this later. Okay, and these all related to the properties of the gas. Okay, because now we have many direction, many chance for choosing one of the direction or velocity. So we need to considering probability or chance. Okay, we need to do that. So when we talk about the probability, we talk about expected value. When everything comes to probability and the number is big, the number is large, so which means that most of the time we will have the expected value to make you see it, okay, appear in the real world, okay, just like the coin tossing problem. If you flip your coin large number of times, it will become 50-50, right? So it's kind of expected value. Right, so let's consider the mean speed. Before we talk about mean speed, we need to see the distribution of a velocity. Here is the velocity, v, low speed, high speed. Remember, notice that in the system, very, very small velocity is with small amount. Very, very high speed with small amount. But most of the population will has normal speed, normal speed for the traveling of the atoms. So you can see this is a normal distribution for the atoms. So this is x is v, low speed, high speed, normal speed. All right. Then let's take a look. What is the meaning of the y? Y is very similar to population, but it's not population. It's the fractional number of molecules. It is the function of V number over total number. N is total number of the contaminant, total number of N. And NV is the number with that velocity. Okay? So the fraction, this is a fraction, fractional number, ratio. Okay, this is a ratio. All right? And the very, very important is that this is FV. FV called probability density function, which is unit. This is density. This is not probability. This is density. This is probability density. Okay? What does that mean? It means that you need to do the integration to obtain the probability. So you need to see that from 0 to infinity, the FV needs to do the integration, make it 1. And this is chance, so no unit. So let me draw the 1. What does that mean, 1? The area under the curve, summing up together, become 1. Okay? So in each segment here, the blue part is actually the fractional number of the molecules in the speed range of V to V plus dV. So FV dV is this. Okay, and FV dV is a probability. It's a probability. If you have a range to make it from V1 to V2, it called the probability for that range, okay, for that velocity. Okay, So you need to be careful. And also, FV is not probability, it's probability density. So the unit is V minus 1 because you need to times the dV to get the probability. All right. So the unit is V minus 1. And so V is actually M divided by S, right? The unit. So the FV has a unit of S over M. So this inverse of velocity. Okay, be careful. So now you know that this is probability density. You need to do the integration from range V1 or V1 plus the range of the V to get the probability. So the mean speed, what is mean speed? Actually, you just do the expected value. Mean speed, V bar, by definition, from 0 to infinity. Oh, don't forget, actually, we has the we have really little chance to get infinity speed of atom, but it has very small chance. So we need to do 0 to infinity. This curve should be look like that, very long, but with really small chance. Okay, so that's why we will have a infinity integration upper bound. Okay, and then V is the expected value. The value for that velocity times its own probability and do the integration. So this is expected value. Expected value is the value times its own chance, right? And sum them up together. That's the meaning of that equation. Okay? And the mean square speed. Mean square speed, by definition, 0, infinity, V square, FV dV. Maybe some of you may ask why we need mean square speed. Why we need this? Because half mv squared. Half mv squared means the kinetic energy. So that's why we need this one. That's why we need mean square speed for later use. It has quite of, energy sense. Okay? But rule mean square, well, it's not that useful, but RMS. So V square bar 1/2. And nth moment, well, by definition, this is not that important, but just tell you the mathematic formulation. All right. Another thing I forgot to tell you, this point is the most probable speed. Okay, I will say V. Should I say P? I don't know. And this is the most probable speed. Okay, because there's the highest chance here. Okay. Well, sorry, I should write down what is the M. Is that M? Most probable. 我要看一下这是不是最大的哦，是 M 啊 ，sorry, it should be M, the most probable M. No, it should be M, the most probable. Right. So that's it. I finished the English lecturing for this page. Now it's time for translation. 这一页我觉得蛮重要的，这就是刚刚讲到这个速度不是平均，不是 uniform 分布，它是什么？normal distribution。这 normal distribution 其实是持续到超远的地方，到无穷大。但是你可以想象，它无穷大的速度，它的几率几乎也是无穷小啊，大概是这个样子。好，那总之它的几率就是从零，就是零积到无穷大。那这张图的意思代表是说，蓝色这一段就是某个速度间距里面它会有的颗数比值。那这个比值呢，把它积分起来就会是它这一个速率之间有的几率啊，好绕口。那总之你把这全部积分起来，它就会是一啊，所有的几率都在这个分布的这个curve 这个曲线的下面的面积，而且它是没有，因为一嘛，它是几率，它是没有单位的，所以你可以想象 v 是速度，那 fv 这个东西叫做它的单位就一定是 v 分之一啊 v 分之一，所以 fv 它不是几率哦，它是几率密度函数哦，所以千万要小心，它一定要乘上，它一定要跟速率来做积分，它才会是变成几率。OK， 好，当然了，这边最高点当然就表示说它最高的几率，most probable 就是最高的几率，对应到的就是它的最大几率的速度。OK， 好，那这张图有什么关系呢？因为它可以告诉我们每一个速率区间它的几率的密度是多少，所以我们可以把它做积分，配合上它自己的值，就可以知道。你看这边是几率，这边是值乘上它自己的几率，加总起来不就是我们以前学到的期望值吗？啊，期望值 （expected value） 就是期望值的意思，期望值。OK，所以呢，做出来以后就可以知道 ，OK，它平均的速度是多少。然后为什么要做 mean square speed 呢？原因是因为这 v 平方，然后乘上它自己的速率，它的几率。为什么呢？因为1/2 mv 平方就是动能嘛，对不对？哈，动能需要我们的 mean square speed。OK，所以这两个是我们常常会在这边用到的，但是后面这几个就比较少用到，我们只是把数学的公式把它写下来。好，总之 这一个页最重要的地方就是 FV 底 V 是在某个速度区间里面，它的颗数的比例是多少？你说一整个系统里面，在某个速度区间里面，它有占几 percent 啊？占几 percent？ Okay, very useful. So when we talk about the fractional number of density, I mean probability density function, FV. Now we are going to talk about how the atoms bump to certain area. So when we talk about when particle bump to certain area, which means that we need to take into account direction, right? Okay, so let's talk about molecular flux. What is flux? The flux actually, the definition is that how many particles flow through that particular area. Okay, we have a symbol phi here. Phi theta. I don't know. The phi, the theta. I don't know what does that mean. What? How to pronounce it? The phi, I don't know, molecular flux. Okay, the definition of the molecular flux is the number of molecules from striking heat a unit area per unit time. Okay, so you can see that. You can also imagine that the number of molecules flow through the area, the dA per unit time. Okay, so the number dN, right? Striking a unit area, dA, a unit time, dt. Okay, so define the definition is the N divided by dA dt. Okay, that's the definition of molecular flux. Okay, so imagine that you have an area like this. Okay, well, dA. Well, this one is equal to this, the same. Okay, just the same. I just give you some. You can imagine that this area has many particles to hit on it. So you can see small v, big V. All right. So what does that mean? The particle will hit that with different velocity. The arrow length represent high speed or low speed. Okay. This is really complicated, right? So complicated. So it's really difficult. We can say this all direction and all speed. Right? So here, I will say, too long. Okay, I will say, hey. So I will say, the conditions here is too difficult. All direction, all speeds, too difficult, right? So I want to make it simpler at the beginning. And then we can, I mean, do the thing step by step. All right. I make it consider one direction and one speed first. Okay. And we only consider this direction. And we only consider this velocity first. Okay, so that's what I'm going to write down here. Okay, only one direction. I only consider this direction. I only consider this V first. And then after we consider this, and then we consider all direction, all speeds. All right. So now this is what happened. So now we only consider this direction and this V. The other we don't consider. So for example, this we won't consider. This we won't consider. All right, the gray one we don't consider. We only consider blue one. So now, how many blue one? How many blue one? actually the particles in this cylinder will all bump to in this direction, all bump to this dA. Why? Because you can imagine that this particle here with this direction, with this V, the V times dt just hit that surface. Okay, but if the particle here with V in that direction, dt will only fly to here, dt, V dt. So it won't hit that area. So only this cylinder will containing the particle will hit that. If the particle is here, yeah, V dt, I penetrate, it's okay, it hit at some point, right? So only this cylinder we need to consider, right? It will hit this area within dt, okay? So we are going to see number of molecular per unit volume is n bar equal to n divided by V. Okay. And we need to times the volume of cylinder. Okay. Now I'm giving you a grade. Okay. So NFV dV times volume of cylinder is actually all the gray points, including the blue one. Okay, all the gray points include, because we only times the n times FV dV is the atom with the velocity v, 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 v. Okay, so firstly we just get the number of atoms in that cylinder, and then I will give you a break. After 10 minutes, I will see you. I will see you after 10 minutes, and then if you have a question, just come here. It comes difficult, so if you have questions, just come here. Thank you. 好啊，还是要跟大家就是讲一下，就是我可能讲过，我不知道，但是我每次都觉得说10分钟的下课根本什么事都不能做不了啊。就我刚刚就是坐在那边喝个水，喝个咖啡，然后上了厕所，就结束了，就10分钟就结束了。然后然后我就在想，我以前小时候，国中的时候，你知道下课10分钟，我那时候跟其他朋友是在4楼，3楼，3楼。
然后跑去操场打篮球，然后再跑回来上课。这10分钟可以做得到，我真的觉得很奇怪，为什么我以前可以，但是现在不行？现在我只是坐在那边上个厕所就结束了。哎，怎么会这样呢？为什么以前可以跑过去打篮球，可以跑回来？那到底只能投几球而已吧？怎么会这样子呢？然后，而且跑很远呢，跑到操场去，再跑回教室，这时间怎么可能在10分钟之内完成？太奇怪了。然后我这就在想了哈，可能我这有讲过了，如果讲过，抱歉哈，因为我老了，我不知道我有没有跟大家讲过这个我自己的乱想。我就有时候会乱想，我就在想，是不是每一种动物的，就是生命的周期，其实在它自己感觉起来是差不多的，因为时间是相对的嘛。就是为什么老人常常就说，哎，演讲的时候，老人常常就会说，哎，我稍微讲几句就好，不要耽误大家的时间。然后哇，讲个30分钟，对不对？为什么？因为他觉得他自己讲很短啊，因为他的速度就是反应太慢了，所以他以为过了1分钟，实际上他已经过了1小时，不然太夸张了。他以为他过了3分钟，但实际上已经变成30分钟了啊，他可能是这样，但是我们就会觉得说时间已经用很久了，但是他不觉得。那我这时候就在想，为什么狗啊、猫啊、动物的那个生命会比我们短？因为它们比我们太灵敏很多了。你看那些鸟，它的头是它头是这样转，所以它表示说它速度很快，它的反应很快，你要去抓它，你都抓不到，因为在它们眼中，我们的动作是超慢，然后它很快，所以它们的生命也会比较短，但它们感觉起来其实跟我们活的差不多长，因为它们速度很快，它们的反应很快。那像乌龟一样嘛，乌龟也是啊，它变得很慢，那它可以活很长。对它来讲，我们的动作都超快，我们都很忙，那忙来忙去，那我们的寿命就比它短。哦，所以我在想，这是不是一个这个地球上的那个动物的这个极限？所以以后如果我们今天要活久一点的话，就要慢慢的做事情。好，大概是这样。好，讲完了。不好意思啊，我常常都会想一些有的没的，然后就是，然后也不知道跟谁讲。然后我每次跟 ChatGPT 讲说，哎，我有个想法，他们都会说你想的真不错，给你很棒的情绪价值，想的真好，对不对？然后我就说哦，对。然后每次问他问题都会说这是一个好问题。那其实我觉得有的时候机器人好不好搞不好会更让你以后陪伴我们的根本大家就都可能都是机器人吧。好，再来，然后我又有想到啊哈，搞不好我们现在生活这个时代是最幸福的时代。哎，有人点头哎，竟然竟然竟然年轻人也会这样想。哎，我们真的是，我觉得我们是真的是可能活在最幸福的时代。但是既然是最幸福的，就有可能是假的，可能是 AI 帮我们设计，你知道吗？你看哦，我们现在活的年代是最好的，原因是什么？原因是因为至少我的啦，我的是从没有到有，没有网络到有网络，没有手机到有手机，没有 AI 到有 AI，这种转变就会让你觉得哇，我的人生好有进步感哦。但是如果今天已经在发展到极致了，你就出生下来就是极致的，你就会觉得这些都是该有的啊，那就没有进步感。好，然后而且到那时候 AI 就取代所有人类，所以实际上人类就没有什么好活的，人类就会觉得好无聊，好无聊，心里就会出疾病，心理出疾病就会不健康，不健康就会做一些傻事，这样。那搞不好，你看我们活在这么好的世界，就是正在进步，而且进步的都是我们还比 AI 强这种感觉。 那这个代表是不是说，实际上这是最幸福的时代？以后到 AI 所有的工作都不用做了，人类就已经失去目标了，其实也不适合活。所以搞不好现在这个时代是最好的，因为 AI 知道人类不能没有目标，所以我们现在活，它就会让所有的人类一直在做这样子的梦，就是从有到没有，没有到有，没有到有，这一段时间是最好的，这样，然后我们就活在这里，就开开心心的，这样的梦境就是最好的。哎，这是我的想象啊，哈，搞不好，对我们都是活在这一个年代，而且实际上我们醒来以后，早就像 Matrix 的那个骇客任务一样，其实搞不好，其实早就是技术已经非常非常进步了，但是电脑为了让我们活得有意义，所以每次都从没有到有这段时间是我们最完美的，又可以好好的努力，让自己好好的诶学习一些东西，然后到最后 AI 可以帮助你，这是最美好的时代，不用到 AI 全部帮助你这样，所以人类还有活着的意义这种感觉，所以这是一个最美好的时代。嘿，我觉得那大家运气不错，那我们就如果是真的的话了哈，运气不错，那我们就好好珍惜这样。好，然后也必须要跟大家讲一下，前阵子在思考这件事情，就是尤其是生小孩以后，就是我要养一个小孩，这其实小孩很脆弱的，那就是要注意所有的事情，一下就可能就会去世，可能就会很恐怖这样，然后发生意外这样，非常非常恐怖，他们非常非常，我们小时候都非常非常脆弱，那这时候我们就在想啊，哈，你看各位，我们各位能活在这个世界上。你要想想看，其实中乐透哦，因为你要活在这个世界上，表示你的爸爸、你的妈妈，还有你的爸爸妈妈的爸爸妈妈，还有他们的爸爸妈妈、爸爸妈妈，弄上去，都可以活到可以照顾到他的小孩子，可以自己活在这个世界上才死掉。哎，这几率很低很低呢，你不觉得吗？就是这几率非常非常低。然后你要回推到生命的起源，你的爸爸妈妈都没有死掉，祖先都没有死掉，你才可以活得了，活在这个世界上。所以实际上我们都是中头彩，对不对？几率非常非常非常低耶。好，就没了。然后就是想到这件事情，其实就是主要就是爸爸妈妈很辛苦啊。哈，大家以后有机会可以尝试一下。对啊，但是现在少子化，就是大家都觉得不要生小孩比较好。哎，没有，我觉得生小孩好，哦，帮政府推广一波，就是生小孩真的是好事啊。虽然你会很累，但有的时候你就会想，如果不生小孩，现在要干嘛？就会很无聊，真的。好，你可以想想看，以后再跟大家分享一些我觉得还不错的人生题。好，在小孩子身上。All right, let's continue. So I just talk about we are simplified the complicated problem into one simpler problem. We consider one direction, one speed first, and then we extend to the left hand side, the difficult problem. Okay, so consider all the atoms with V, and only one direction. One direction. All right, but one direction, only the atoms in this cylinder has possibly to hit this area. Okay, so N is the number of molecular per unit volume times the velocity probability, right? FV times the volume of the cylinder. Okay, but this considering all the direction, not what we want. Okay, at this moment, not what we want. Okay, so continue. Equal N divided by V times FV dV. This is possibility, right? Times V dt times cosine theta times dA. Okay, of course, this is cylinder volume. Okay, V dt, it need to become height. Height need to be times cosine theta. Okay, times cosine theta. Theta is the angle between the z-axis and the velocity direction. All right, times dA. But this is for all the direction, but only a few of these molecular will travel toward the A in this direction. So only a few of these molecular with this blue highlighted direction. Only the few. So, which means that they are all. We don't want all. We want one direction. So, times a factor, the ratio. This ratio, including only a few. For example, maybe 25% of these gray atoms, 25% will hit that direction. So this should be a factor, 25%, 40%, I don't know. We will determine that in the next page. Okay, next page we will determine that. 好了，这个越来越难哈，跟大家讲什么叫做分子流量。所谓的分子流量就是你有一个单位面积，在单位时间内有多少颗撞到它。所谓的撞到它就是流过去的意思吧，就流过去，撞到它就流过去了哈。好，那这是它的定义。所以单位时间、单位面积有几颗撞到它，就这样。好，这是它的定义。但是呢，理论上来讲，你看到这个 dA， 你会看到有好多个速度、好多个方向都会撞到它。要怎么算？超难，对不对？哈，超难 ，all direction, all speed， 超难。所以我们先做简单的，我们先看一个方向，一个速度，好不好？就这样，先看这个。所以呢，一个速度就写，我们选 v 这个速度，一个方向我们就选这个方向，这个方向跟 z 轴加西塔角。OK， 好，我们先看这一个。那我们要看是这个如何来看呢？我们想象一下，哪些颗粒会撞到这个面积？只有在这个桶状里面才有可能。为什么？因为你想想看哦，假设就是这个方向可以了，这个方向当然不用提啊，这就不会，它就飞走了哈，不管它啊。但是如果今天它是朝对的方向，你看这一颗正好在这个边缘的时候，它飞向底 A， 正好底 T 的时间 ，V 底 T 的时间正好刚好碰到它，哎，它就碰得到了。但是如果今天它在这里，哎，它就飞那么久，它会超过啊，会撞得到。但是如果今天它是这么远，哎，飞不到就停下来了，时间就到了，所以它撞不到。所以只有这一个桶状里面才有可能撞到它，而且是要这样子的方向才可能撞到它哦。好，那接下来，所以我们就说这个桶状里面有几颗原子啊？是这个速度的呀。好，那就是平均的颗数在单位体积下，因为它是 uniformly distributed， 它是没有任何的偏心嘛，哈，所以它的分布是均匀的 ，n 除以 v， 乘上它的体积就会是它这一个空间里面的颗数，再乘上它的速度的几率，就会是这个值，就会是这里面所有颗数有 v 这个速度的颗数 ，OK？ 但是又不是全部，你看灰色也飞走啦，只有蓝色朝这个方向才是对的。所以 可能，例如说有20% 在里面，有25% 会往这边飞。假设了哈，比如说你必须要乘上一个数字，乘上一个比例，它才是真正会往这边飞的。OK， 那下一页我们就要算出这个比例是多少。OK，so next page we are going to determine what is this question mark. So this is that question mark. Okay, we are going to determine this question mark. But how? Okay, remember the sixth assumption. Direction of the velocity are uniformly distributed for these molecular with velocity v2, v plus dv. Okay, so imagine that all this particle has many direction possibility. This, that, every direction. You can imagine that the direction can be forming a ball, a sphere. Okay, this is a sphere. All the direction v with the radius v, because you are focusing on one speed, right? So all the speed forming a speed sphere. This is a speed a space, or you can say speed well, or you can say speed ball, anything. Okay, the speed space, possible space, speed space looks like this. And now we are going to determine one direction. For example, this direction, the red, one direction. Of course, in the previous page, we are talking about this area. But well, when you determine this, you also can receive the same value, right? Because they are all uniformly distributed. So we only choose one direction. So which means that it actually is a one tiny dA for all sphere area. That's it. The ratio. Okay. So now we are going to determine dA. What is dA? Or we can say d sigma. Sorry, d sigma. We cannot say dA, otherwise we will mix with this. Sorry, we should say d sigma. Sigma is the red area, one direction, one specific direction among all the direction of the speedball sphere surface. Okay, so the element of the area of the surface of this speed vector sphere is the sigma. The sigma, what is that? The sigma. How to obtain a d sigma? This is the sigma. The d sigma is here. All right. Okay. So let's take a look. Yes, this is the z-axis. That and that. So this is theta. Okay, theta. And the open is d phi. D phi. Okay. And of course, this is v vector. Okay. And you can see that, let me take a look. Oh, this length
is V sine theta, right? V sine theta. So the V sine theta, can we see that V sine theta, V sine theta. So this curve, this shape curve is V sine theta times the phi, because the open angle, okay? And how about this? This is actually the height of the sigma is V the theta, because you can see the V here open, kind of doing the small angle along the theta direction. So here the open angle is the theta, right? So I will say difficult. Yeah, here will be the theta. All right. So that's how we obtain the height of the sigma. V sine, the area of the sigma is V sine theta d phi times V d theta. Actually, what I'm doing is calculus. V sine theta d phi times V d theta, right? And V squared sine theta d theta d phi. Okay, so now this is one tiny d sigma. Okay, and then we want to obtain entire sphere. So we do the sigma times, integration sphere. So when we talk about theta and phi for all the direction, you can obtain all the sphere area. Okay, so you see this one is here, and the theta from theta to the phi. Okay, the phi. We need to do this how to say 0 to 2 pi. Okay, 0 to 2 pi, no problem, right? And here it should be theta should be minus half pi to positive half pi, okay, to make it circle. But you will notice that this minus this half, it will make it 0. Okay, so we cannot do that. We need to make it 0 times 2. Okay, so you can see that the the yellow should be 0 to here. Okay, and the green one here need to be 2. Otherwise, it will cancel each other. Okay, because half pi minus positive half pi, do the integration, it will be exactly 0, because they will cancel each other, become 0. But we are going to get the positive area, so we need to make it 0 and times 2. Okay, and you see that, oh, this is 4 pi v squared. Okay, the reason why we do that is to avoid negative area. Okay, so now you see that here is I will say this is one direction. This is all direction. Okay? So we want to get the ratio between them, d sigma, and 4 pi v squared, 4 pi v squared, and d sigma v squared. So, okay, so that's exactly what we want. Okay, so see, this is the direction we want. And this is all direction. Okay, that's it. 好，这一页全部都，我们这一页都有点跳出，就是 molecular flux 这件事情。我们在着重在于那个蓝色的那个问号的比例到底是多少？到底有多少比例是往这个方向走，而不是那些灰色的往别的方向走的？那既然所有的方向都可能，表示说这个那个速度的向量可以把它画成所有可能向量都可以画成一颗球。所有的方向是 v 这个长度的速度向量都可以找到那个球，那我们只要一个方向就好了的比例是多少？好，那这时候我们就是要先做积分嘛，哈，一个方向是 d sigma， 全部的方向就是球的面积嘛。那这边我就把一个方向的一个微小的方向的比例算给大家看，是 d sigma。然后 d sigma 就是一个方向的比例，一个方向的面积。那所有方向就是整个 sphere 整个球体的面积。好，那要算，那算完以后，我们就发现我们的那个上限下限要小心取，因为我们看这个 phi 嘛，哈，这个不对 theta 是这样子开嘛，这样子开，所以我们都会假设我们就从这边负2/π开到正2/π。就可以是这个面，然后在这个面再转一圈就是全部的面，但是不行，原因是因为2/负派、2/π还有负的面积，所以一积完以后它会变成0，那不行，所以我们要把它改成0到2π再乘以2。好，那乘以2完以后呢，再做一圈就会是4π v square， 就是所有的方向的面积，所有方向面积放分母。单方向 one direction 当分子，那你就可以得到问号这个比例是多少？也就是说，分子就是我们想要的方向，分母就是所有的面积，所以这个问号就可以带到这里来了。All right. So now we finally knows that our dn equal to blah, 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 blah times the vector. Okay, finally. So let's continue. All right. The definition of the particle flux is this one, right? So we notice that, okay, we can cancel the A. Okay, we can cancel the T. Okay, so the only thing left is this one times this. Very when we use this, you see v f v dv, v f v dv, and cosine theta, sin theta, d theta, d phi, sin theta, cosine theta, d theta, d phi. Okay, so everything here comes here, and then we do the integration. Okay, integration from 0 to infinity. So we do the integration for the boundary. For v, yes, 0 to infinity. For theta, yes, 0 to ½ pi. For phi, 0 to 2π again. So this is the formulation after this. Substitute back and do the integration.
And here is V bar. Nice. We just get the definition, right? Expected value. And here is pi. Well, you can go back home to derive this. And then finally, we know that equal to 1/4 n bar V bar. Vn on the bar V bar. OK, finally. 好，我们要讲的就是，终于把这个比例算出来了哈，把这个单方向的比例算出来了。单方向的比例乘上这个所有的方向，就会是打到那个体积的面积的地方。好，那我们再去看看底 n 底 a， 怎么讲 ？flux 它的定义是底 n 除以底 a 底 t 嘛哈，所以底 a 底 t 就消掉了，所以底 phi 就是写出来就写在这里。但是我们发现，哎，不要忘了有所有的速度跟所有的方向哦。So I forgot to say this is all speed. This is all direction. OK， 所以代入以后呢，我们就要去积分所有的方向跟所有的面积，所有的速度。所以你看，这所有的速度0，刚好这边有 Fv 底 v 乘上 v 嘛，对不对哈？那这个东西做对所有的速度积分，它就是 v bar 啦。那所有的方向，那这边就是西塔要从0到2/π，然后 phi 要从0到2π啊，全部做完积分，就可以得到派，得到全部的 molecular flux 就会是这个分子的流量就会是1/4 n under bar v bar。好，算完这个东西哦，好难算了哈。也就是说，它的分子流量就是1/4 n under bar v bar。OK， right. Why should we do that? Why should we do that? Why? All we need to know is that how frequent the velocity and the direction can hit that area. Why we need to do that? Because the hitting collision for particular area is useful for determining some material properties that we are familiar with. Okay, here, gas pressure. Because we are talking about gas pressure means that the gas atom bump into the container wall. So the wall will feel the pressure, feel the bump, and then it generate the pressure for what we see, right? Okay, so okay, so the definition will be, you can see that the definition of the pressure is the momentum, the change of the momentum. You see that this is pressure, capital P is a small p. The small p is momentum, okay, momentum here, the change of momentum. So, sorry, this is mistake. It should be d small p. Okay, this is momentum. Momentum. All right. Momentum. Momentum is mv, right? Mass and velocity. Momentum. The definition of momentum. So the change of the momentum at the constant. At constant. Unit time and unit area is the change of the momentum at unit time and unit area is the definition of the pressure P. So let's take a look. The change of the momentum for the particle bump into the wall and do the perfect bumping, perfect collision. So it's mv and mv prime. What will it change? Okay, so the change of the momentum of one particle. For one particle, particle bump and then go down. What is the changing of the momentum? What? Actually, you can imagine that this movement can be decomposed into up and right hand side, and right hand side and downward. Okay, so you can see this direction can has horizontal component and vertical component. This one also horizontal and vertical. Blue, not change. So it doesn't count into the change of momentum. It only counts up and down. So this is the only thing they change. So vertical direction is something they change the momentum. So the momentum, the change of momentum is mv cosine theta, the theta, m theta. mv cosine theta, this is upward positive. And this is minus mv cosine theta. And the change will be double 2 mv cosine theta. So each particle bump into the wall and it will generating 2 mv cosine theta changing of momentum. Okay? So this is one particle, 2 mv cosine theta. But now we are going to determine all the velocity. Okay, all the velocity. So we can see the dn here. dn here is the, if we write down like this, dn is actually, wow, dn is n under bar fv dv v dt cosine theta dA times sine theta d theta d phi over 4 pi. Okay, remember this long ugly definition, the n from the previous page, right? So this is one direction. Sorry, yeah, one direction. One direction. And you need to do integration, all direction. Okay, for the integration. So now, and also all speed, right? All speed. So we need to do one direction, one speed. So this is one direction, one speed. We need to do integration just like previous. So you see now v squared times n, and some constant go out to the integration symbol called v dv. Okay, you need to do the 0 to infinity. So you see v squared. This is the Riemann mean square velocity, right? Here. V squared. Okay, and of course, the theta the theta is for 0 to 2 pi, half pi, and 0 to 2 pi. Okay, and this, the value is 1/3, and this is 2 pi. So after we sum them up together, times together, it becomes 1/3 n under bar and v squared bar dA dt. And this I believe you know what is n on the bar, n over v. Okay? Then the p substitute here, dA dt, dA dt, luckily, Okay, so pressure times V equal to, you can see the N here is N over V. Okay, so if we put the V to the left-hand side, okay, so you have PV equal to 1 over 3 N MV squared bar. What does that mean? Let's take a look. 2 over 3 half M V squared. Okay, so you see 2/3 of average translation no kinetic energy. Okay, so our PV equal to this value. What does that mean? It's actually 2 over 3 average translational kinetic energy, half mv squared. All right, half mv squared. Okay, that's it. Oh, by the way, the m here is 1 particle mass. Okay, 1 particle mass. So that's the half total m v squared. Average translational kinetic energy times 2 over 3, you have PV. Connecting to what we learned before, PV, right? Related to MRT or work or something. 好，我们刚刚算了那么多什么 molecular flux，其实最重要的是为了要得到这个东西，就是一个方向一个速度的表示方式。然后啊，气压其实就是在单位时间、单位面积下，它改变的动量的改变，动量改变量 ，OK， 动量的改变量，它的定义就是这样。那我们就看一颗会怎么样改变。一颗原子撞到它以后，它是这样，就是它是完美的撞嘛，哈。那你就会发现蓝色的分量是不变的，它只改变红色的分量，一前一后，或是一上一下。假设上是正的，下是负的，它们相差2个 2 mv cosine theta 的动量改变量。好，那是一个方向，一个方向一个速度。那我们刚刚才算出来 dn 一个方向一个速度是长这样子，那它的动量改变量是这样子。我们要把它变成延伸成所有的方向跟所有的速度，当然就是做积分咯。好，我们做一样的积分，我们就会发现这边跟这边的值都算出来啦，算出来答案是这个，底 P 就会是长这样子，底 A 底 T 消掉了以后呢，我们就会发现，然后把 n 除以 v 这个移到左边去 ，PV 就等于1/3 nmv 平方 bar。m 是一颗一颗气体分子的重量，质量，这是颗数，所以我们就会发现这个1/3其实就是2/3乘上它的动能哦，2/3乘上动能，也就是说 PV 会等于2/3乘上它的动能。这 good to know 这蛮好的一个资讯。Right. So gas pressure and the ideal gas law. So you see PV equal to MRT NKT. Yeah, this is ideal gas law, no problem. And Boltzmann constant, K equal to R over NA. Yeah, I guess you know that the Boltzmann constant. We introduced that and we will use this quite often later. Okay, so we notice that actually for an ideal gas, NKT is equal to 1 over 3 mmv square bar because you can see PV NKT. PV equals NKT equal to PV, right? PV equal to 1/3 mmv square bar. Or you can say 3/2 kT equal to the kinetic energy of molecules. Yeah, just rephrase it. At room temperature, 3/2 kT equal to this 0.038 EV. So typically, the kinetic energy, the movement, the kinetic energy of a molecular is typically 0.038 EV. So what does that mean? It actually means that previously we draw that figure, right? Vx and R, and we have the curve like this, right? And actually this height typically is the kinetic the molecular has, right? So the delta E is for potential well is commonly within this value. 好，我们把刚刚的得到的结论哈，就是 PV 等于 nRT NKT， 这是我们原本就会的。应该说 PV 等于 nRT 我们原本就会了哈，但是 NKT 其实就只是换一个方式写，这 K 是波兹曼常数，之后我们会常常用到。那我们这时候就写 OK K NKT 会等于 PV， 那 PV 又等于这个1/3m， 我们刚刚前面才写过的 OK， 然后我们再算一算，我们就发现哦，2/3 KT 会等于它的动量，应该说动能量、动态能量、动能。好，动能就是1/mv平方嘛，哈。好，那这时候这个动能，还记得我们那时候说动能就是每一颗的动能，其实基本上就是它这个 energy well 的深度吗？因为它跑来跑去，结果你有一天终于安稳的在那个地方留着了。那你要让它离开，你一定要给它推动足够的动能，才能让它离开。那这个 energy well 就是它的动能，你把它推离开这个地方，所以正好就是它的动能嘛，哈。你要刚好它的动能才可以离开它。所以如果今天在正常温度的状况下，你的 energy well 大概就是这么大啊，0.038 EV 左右。那真实世界来说，对，没有错，真的就是在这个范围之内，所以它可以给我们一个好的估计值。OK， right. Next, we are going to talk about molecular degrees of freedom. Okay, degree of freedom means that how a molecular can move, can change its shape or its position. Of course, it related to energy. Okay, so there are 3 types of motion of the molecular. We can imagine that the molecular can be simplified as a bead, ball, and spring. Bead spring model. Okay, because they connected to each other. So they kind of spring. And this is atoms. So this molecular can move in the XYZ space. Okay, it's called translation. Or it can rotation. Okay, or vibration. Okay, so these 3 types of degree of freedom define the motion of the molecules. 分子的动态可以有3种，第一种是移动，第二种是旋转，第三种是震荡。OK， 我们把它想象成是2颗球被一个弹簧连在一起，所以你就可以想象这2颗球跟弹簧怎么这样在这个世界上移动。那就接下来就会用这个方式去学习、去解析分子的动态。Okay, so I think that's all for today. Thank you for your cooperation. I will see you next week. Thank you. Yeah. Okay.